Hi everyone, welcome to this session on linear independence. So here we are talking about a set of vectors and we want to check whether they are linearly independent or dependent. Assume we have a set like this, x1, x2, x3 and x4. We have four vectors, x1, x2, x3 and x4. They are independent or dependent. Suppose I can represent x3 in terms of x2 and x4. Suppose I can represent x3 like this. That means that x3 is depending on a value of x3 is depending on x2 as well as x4. So there is a dependency among these vectors. So we say that they are linearly dependent. Okay, they are dependent. And if there is no such relation between these vectors, we call them as independent. Okay, that is actually independence or independence all about. Now we can see, we can start with the unit vectors. What are unit vectors? The quantity or the magnitude of the vectors is 1. So that kind of vectors are called unit vectors, and consider the unit vectors I and j on xy plane. So I is the vector on x-axis and j is on the vector on y-axis. Okay, we can represent any vector in the xy plane using I and j. That means we can represent any vector as a linear combination of I and j. Sometimes we can extend or we can multiply I with a scalar value, we will get a vector, or we can add I and j, we will get another vector, like that. Okay, so using vector addition or scaling, we can reach or we can represent any vector on the xy plane. So for more clarity, you can visit this YouTube channel that gives you a graphical representation of this thing. Okay, how to represent any vector using I and j. Then come to bases, and what are bases? So a set of vectors with which we can represent every vector in the vector space is called a basis. Okay, basis is basically a set of vectors. Using those vectors, you can represent any vector in the vector space. For example, I and j, the unit vectors in xy plane. So using xy, we can represent any vector on the xy plane. So we can also take non-unit vectors as basis. I and j are unit vectors because their magnitude is 1. We can take any vector whose magnitude is not equal to 1. Okay, that also is possible. So consider the vector space V and a subset of it X. Okay, the vectors inside X can be represented as x1, x2, etc. xk. So we can call it as a basis if we can represent the vectors on V, like V1, V2 and V3, or any number of vectors can be there in the vector space V. We can represent each one of it as a combination of these vectors x1, x2, etc. xk. Okay, so for example, a v1 can be represented in terms of x, that is the vectors x1, x2, x3, etc. xk. Similarly, v2 can also be represented in terms of x1, x2, x3, etc. And v3 also. Okay. So the coming to the term linear combination, consider the vector space V and the basis vectors x1, x2, etc. xk belonging to the V itself. Then every vector in V can be represented as a linear combination like this. In any vector on V can be represented like this: lambda 1 x1 plus lambda 2 x2 plus etc. lambda k xk. So any vector on V can be represented as a linear combination of the basis vectors and real numbers. Here this lambda 1, lambda 2 etc. are real numbers. Okay, and this is called the linear combination. So we can represent any vector on V as a linear combination of the vectors x1, x2, etc. xk. And in this case, this x1, x2, this set may not be a basis set also. Okay. And linear independence, when we find the solution for this linear combination, we assign this linear combination as 0, lambda 1 x1 plus lambda 2 x2 plus etc. lambda k xk to 0. And when we find the solution, that is, we already know the values of x1, x2 and all. So here the unknowns are lambda values. Okay, lambda 1, lambda 2 up to lambda k are unknowns. So when we find the values for these lambdas, if at least one of the lambda is not equal to 0, then we can say that the vectors x1, x2 up to xk are linearly dependent. Okay. And if all the lambda values are 0, then these vectors are linearly independent. Let's see how it comes. Okay, in short, every vector in the set x1, x2, etc. xk has their own role to represent any vector in V. For that, we can assume, we can take this equation once again, lambda 1 plus lambda 2 x2 plus etc. lambda k xk is equal to 0. And we assume that here lambda 1 is a non-zero. When we find the values of lambdas, lambda 1 is non-zero and all other lambda values are zeros. Okay, then what happens when we substitute the values for lambdas here? The equation will be reduced to lambda 1 x1 equal to 0, because all other terms getting cancelled because the lambda values are 0. Okay, then we assume that lambda 1 is non-zero. Then to make this equation satisfied, this x1 should be 0. That means x1 vector x1 is a 0 vector. So 0 vector cannot contribute in addition or scalar multiplication. Okay, so without x1, I can represent any vector in V. So x1 has no role in deciding a vector or representing a vector. Okay, I can graphically represent it like this. Suppose vector v1 can be represented with x2, x3, etc., xk and not x1. Okay, I don't want x1 to represent the vector v1. x1 has no role in representing v1. Okay, in this case, we can say that this set x is linearly dependent. That means that there is one unwanted vector there in this set. Okay, so that means that without x1 also I can represent the vectors. Then why do we need x1 over here? If we remove x1, this x will become a basis vector, set of basis vectors. Otherwise, it will not be basis vector. Okay, so since this redundant vector is there, we call it as a linearly dependent set. Okay, and x will no longer be a basis set. And what is the intuition behind this linear independence? There should not be any redundancy in the set of vectors x1, x2, etc., xk. That is, only necessary vectors should be there in the set. If there is any vector that is not necessary to represent any vector on the vector space, we can remove it, or we call it as a redundant vectors. Okay, as we did in the last example, that is here x1 is a redundant vector because x1 is not necessary to represent vectors on V. Okay, so if x1, x2, etc., xk are linearly independent, then there will not be any redundancy. Okay, if we remove any vector from x, then we cannot represent the vectors in V. So that should be the condition. All the elements in x should be necessary elements, necessary vectors. And redundancy is example given like this: x1, x2, two vectors are there. And how to represent this one? This x3 is actually representing x1 plus x2. Okay, so to represent the vector, this this dot 1 is the vector. In order to represent that vector, we can use x1 and x2. Okay, x3 is not necessary there. So I can represent this vector in terms of x1 and x2. This point can be represented as x2 plus x1. Okay, it is x2 plus x1, and this x3 is totally unnecessary. And even if I remove this x3 from the set, from my set x, still I can represent the vector, this vector. Okay, so x3 can be considered as a redundancy. When I remove that x3, the set becomes this set becomes linearly independent. Okay, from this set, if I remove this one, it will become linearly independent. Okay, now assume the vectors x1, x2, x3, x4, x5, 5 vectors are there. If I can represent x3 in terms of x1 and x2, that means there is a dependency. That's what I said earlier. There is this value of x3 is depending on x1 as well as x2. So there is a dependency. Based on the values of x1 and x2, x3 is also changing. So there is a dependency. So this set, and this entire set will not be independent. They are called linearly dependent. Okay, so the set of vectors are linearly dependent. So when we remove this x3 from the set, we can make it as a linearly independent one. Okay, and x3 is the redundant vector. So if we can define it like this: if any xi cannot be represented in terms of other vectors in the set x1, x2, etc., xk, then the set of vectors x1, x2, etc., xk is called linearly independent. Okay, then the properties to check the linear independence. There are some properties when the sets, when the elements of a set are linearly independent. K vectors are either linearly dependent or linearly independent. There is no third option. Okay, when we take a set of vectors, they can be linearly dependent or independent. Okay, if at least one of the vectors in X is 0, then the vectors in X are linearly dependent. That's what we have seen in the last example. When lambda1 is non-zero, then x1 becomes 0 vector. So 0 vector cannot contribute in the representation of any vectors. So if the set, if we have taken a set X like this, inside that we have a 0 vector, then definitely we can say that this is linearly dependent. Then the same holds if the vectors, two vectors are identical. Even in the set X we have identical vectors, then also we can say that they are linearly dependent. So the third property is the vectors in X are linearly dependent if and only if at least one of them is linear combination of the others, as we did in the last example. X2, x3 can be represented as x1 plus x2, or I can say x3 is a combination or a scalar of x1. Okay, both are considered as linear combination. Okay, something like this, where lambda belongs to real numbers. And how to find out the linear independence? How do we do if a set of vectors are given? How we can find out they are linearly dependent or independent? For that, we use Gaussian elimination, as we did in the last classes. Write all vectors as columns of A. Okay, A is the this is the vector representation of the homogeneous equations. In this, this vectors are returned as this coefficient matrix. Okay, all vectors as columns. Okay, columns of A. Then find the raw echelon form of A. Then the pivot columns indicate the vectors which are linearly independent of the vectors on the left. Okay, all the pivot columns, the columns which contains pivot elements are representing linearly independent vectors. And non-pivot columns can be represented as a linear combination of pivot columns on their left. That means that when you reduce this A, if it contains any non-pivot column, then it is linearly dependent set. Okay, if all the columns are pivot columns, then it is linearly independent. Okay, so let's see an example. So this is a matrix after reducing A. Okay, then we can say that this is a pivot column and this is a pivot column. These two are pivot columns. Okay, so these columns represents the variables x1 or vectors x1, x2 and x3. So this means that x1 and x3 are linearly independent vectors. Okay, and x3 is actually depending on the vector on his left hand side, that is x2 can be represented as 3x1. Okay, x1 x2 are linearly independent and x2 can be represented as 3x1. Okay, it depends on the left hand side vectors. Okay, x2 depending on its left hand side vector. So x2 can be represented in terms of x1, 3x1. Okay, so we can say that the set x1, x2, x3 is linearly dependent. They are not independent because there is a non-pivot column existing here. Non-pivot columns represents the dependent vectors. Consider another example of R4. We have three vectors from R4. Four elements are there in each vectors. In R4 that is the case. Then let us represent the linear combination like this: lambda 1 x1 plus lambda 2 x2 plus lambda 3 x3. So it is written like this. And how to find out the solution, or how to find out they are linearly independent or dependent? So we have to make the vector A. We have to find out the vector A. Then how to find out? Here this vector A is representing the vectors and X is representing actually the lambda values. Okay, lambdas are the unknowns here. So we have written vector A like this. The coefficient vector A like this. How do we get this? We have to go back to this. Okay, you take each vector x1, x2 and x3, and in the matrix A, the x1 represents the first column and x2 represents the second column, x3 represents the third column. So we have to write x1 over here, that is 1, 2, minus 3 and 4 over here, and 1, 1, 0, 2, that is x2 over here, and at the third column negative 1, negative 2, 1, 1. Okay, we have to write like this. So that is the matrix A. Okay, or the quotient matrix A. So it is written here, and now we have to reduce it into row echelon form. Okay, I applied minus 2 r1 plus 3 r1 and 4 minus 4 r1. Okay, this transformations have been applied and we got it like this. So at the first column we got 1 and all the remaining elements in the column are 0, and then minus r2, that makes the second pivot element. We got the next pivot element, then we have to make the other 3 and minus 2 to 0. So we applied this transformation and we got it like this. So we got 2 pivot columns and the remaining values are 0 over here. Now we have to make this minus 3 as 1. So this operation is applied and we got it like this. And we have to make this 5 as 0. So we applied minus 5 r3. So the final answer is like this. So that means that every column has a pivot value. Here we have a pivot value, here also we have a pivot value, and here also we have a pivot value. So these pivot values, since all the columns are pivot columns, this is a linearly independent set of vectors. Okay, so here the columns, every column is a pivot column. So the vectors x1, x2, x3 are linearly independent. Linear independence. In this previous example, we consider only one equation So we consider only one equation. Now, if there are m linear combination of k vectors, x1, x2, etc., sk, how do we find the linear independence? Okay. So, suppose the vectors are written like this. Vector x1 is written like this. b1 minus 2, b2 plus b3 minus b4, like that. So, here b1, b2, b3, and b4 are linearly independent vectors. Okay. And using those linear independent vectors, we are representing our 4 vectors x1, x2, x3 and x4. And how do we write the vector A? Okay, so as we already know, vector in matrix A, every column represents a vector x1, x2, x3 and x4. So in the first column I have to represent the vector x1. So how do we represent vector x1? Take the coefficients of these b vectors b1, b2, b3, etc. So the vector here, the coefficient is 1, so that has to be written here, and here the coefficient is minus 2, that is to be written, and here the coefficient is 1 and minus 1. Okay, then take the next equation, next vector x2, then take each coefficient. So we will get the matrix like this. This will be the matrix, and each column represents each vector x1, x2, x3 and x4. Now we have to reduce it into row echelon form, and the reduced form is like this. Okay, and so we can find pivot columns here, first one, second one and third one, and the fourth one is not a pivot column. Okay, that means x1, x2, x3 are linearly independent, and x4 is depending on the other 3 vectors. Okay, that means that x4 is depending on x1, x2 and x3. x4 can be written like this. How? Minus 7 into x1, minus 15 into x2, minus 18 into x3. So x4 can be written in terms of x1, x2 and x3 like this. Okay, so that means x4 is depending on the other three vectors. So the set x1, x2, x3 and x4 are linearly dependent. Okay, there is a dependency among x1 and the other 3 vectors. Okay, so there is a dependency. They are linearly dependent. Okay, so that is linear dependence and independence. Then coming to the summary, we have seen basis vectors. So basis vectors are the vectors with which we can represent any vector in the vector space. In linear combination, we can represent any vector as a linear combination of the basis vectors. Then linear independence means if there is any dependency between the vectors, we call them as linearly dependent. And if there is no relation between then any dependency between the vectors, we call them as linearly independent. And we found how to find out the linear independence or dependence of the vectors using the Gaussian elimination method. That's what about the linear independence.